Welcome to another video in the tuning series. Today we are going to talk about two different things which can be pretty important but aren't really necessary for the bass tuning. Which is, first of all, acceleration enrichment, so basically the throttle response settings, if you can call it that, and also EGO control, which means Lambda control, or rather how much the Lambda sensor or the ECU is going to control the fueling by looking at Lambda values and seeing if it's too lean or too rich at that point. First of all, we want to look at acceleration enrichment. What is that used for, or what is it? It is used for getting the throttle response better. So when you are on tip in, which means when you depress the gas pedal at a faster rate, it happens if you do not have extra fuel injected, is that the engine kind of hesitates when you do that, especially in cold situations. When warmer and on higher RPMs, it's not that big of an issue, but in colder environments, or generally when the engine is colder, and in addition to that, when you, depending on how much and how fast you press the gas pedal, this can be quite bad. And you can fix that with acceleration enrichment. While there are standard tables that are turned on in the ECU base maps, which kind of work, they make it a lot better than completely without those maps or completely without acceleration enrichment. There's still room to improve, not only in the amount of fuel, but also in the duration when the extra fuel is actually injected. And that's what we are going to have a look at now. So first of all, looking at the acceleration enrichment, I have already opened the tab to adjust everything that is needed. If you have bad throttle response and already tried acceleration enrichment, as I said in a previous video, you can go to engine constants and there set map sample method to either instantaneous if your car doesn't have the lower map sample switching point, or event average, and set the switching point to something like 3000 RPM, so that it goes below that is instantaneous and above that is cycle average or event average. The reason for that is being when you are under load or on higher RPM, you want a more precise map value that isn't fluctuating as much as with instantaneous, and this is why you choose event average there. But for better throttle response, the instantaneous one is going to be better at a lower RPM. All right, then going to acceleration enrichment. I'm going to show you a clip which has basically no or bad acceleration enrichment, and you can judge basically for yourself and see what the problem is. And this is basically what you are seeing, or what you would be seeing when you have no acceleration enrichment enabled, or just not the right settings. Enrichment mode, I would always choose TPS because I haven't got the maps-based acceleration enrichment working yet that well, so I would recommend TPS based. So depending on how much percent the throttle pedal position changes per second, so this is TPS per second, so TPS dot, if it changes 10% per second, and you might wonder why it is like 1000 up to 1000% per second. If you would step on the gas really fast, like within 0.1 of a second, then that would be 1000%, because within 1 second you would be changing the TPS value by 1000. So that's kind of the logic behind the TPS dot, and very often you are going to get over the 100% value. With the values themselves, try around a bit. Usually it's going to be somewhere around 20 to maximum 100% enrichment, and the lower values depends. You can try and play with the throttle a bit, and then you see a green dot jumping around here, and see where that actually lands and what you actually need to adjust. Usually it's going to end up around 500, and then you just set a nice curve. I'd say like 300, 200, or let's do 150, and then 50 or something. And then for the enrichment, this depends heavily on what application you are running. So if you're running ITBs, for example, you're going to have to use more fuel, because on a lower throttle opening, the engine is going to see more air than with one smaller or one throttle body that still is bigger than 4 of the individual ones, but still it's not going to flow as much air when just opening a small percentage. So you might need to try around a bit. Usually a good starting point would be like 25, then 50, 75, and maybe 90 or something. You will have to, again, as I said, try around with that. The issue is you will have to look at that while driving, or rather see if it drives well, because on a standstill, the throttle response is going to be different than when driving. So to test that, basically drive at maybe 2000 RPM and then give it some throttle and see if there is any hesitation, or if it gets better when you adjust down or up. And again, you'll have to try around with that. You can also watch your AFR gauge. If it gets really lean, like in the AFR 1920s while you press the accelerator, then this is going to be not enough fuel. If it only gets to like 15, 16, or maybe even 17, then you are pretty close to being good. It is going to be leaner than your target AFR, because if you would adjust it so that it is the same, or rather like an AFR value that is close to that, it's going to be pretty much too much fuel to get the throttle response correct. So I would rather stay on the leaner side, because that works best in my experience. Then we have some other options. So we have the TPS.threshold. So this depends on where the ECU will actually start to add fuel. While yes, on a very little input, or very slow input, you don't really need it. Though I would set this to like somewhere around 20 to 30. This also depends on what you are seeing. Minimum TPS change, you can leave that at 1, because otherwise it might be adding randomly fuel while you are just driving around, and that might not be that desirable. Acceleration time, 100 milliseconds is usually pretty good and enough. I wouldn't go shorter, and longer is not really needed most of the time. Although you could try if you are seeing a really lean spike for a bit longer, but still 100 milliseconds usually is plenty. Then there is start taper, or taper start and taper end. While most engines on higher RPMs, so I would say above 3000, don't have any issues with acceleration enrichment, because it is the engine is producing or is getting enough fuel to wet the cylinder walls to get a good air-fuel mixture within the cylinder. On lower RPMs, you are going to have to inject some extra fuel, which we are doing with the acceleration enrichment, and you can taper that off. Usually I would say it's going to be best to set that at 2000 and something like 3000. It's not too bad if you set this a bit higher, as it's just going to be working at a higher RPM, and usually it's not going to be that bad. Then we have the acceleration enrichment cold adjustment. This is pretty important, because when a engine is cold, it is going to need more fuel being injected for acceleration enrichment. Usually 100% is 0, so
That's basically the same values we have here. In my experience, somewhere between 150 and 180 is going to be ideal. Also depends kind of on your injector size. If you have very large injectors, it may be enough to select a bit less. And then you also have the start to end taper temperature. That is usually, I would set this to like 20 or maybe 20 to 60 is usually fine, and above that coolant temperature, the engine will get a lot better throttle response anyway, and those values that you have selected on the left side will probably be enough. That's it for acceleration enrichment. Next thing is Lambda control. Basically, every normal car with a normal ECU has a Lambda control built in. So that means if the ECU, no matter if it's a narrowband or wideband sensor, but especially on a wideband sensor car, the ECU has a lookup table for Lambda driver's wish or AFR driver's wish, which is basically the AFR value on which the car is supposed to be at that moment in time, or rather at that throttle position, map value, or RPM, or whatever the case may be. And obviously the ECU reads the Lambda value from the Lambda controller that takes the value from, or the voltage from, the sensor and gives that out to the ECU, and the ECU adjusts or fuel accordingly to get the current Lambda value to the driver's wish Lambda. So that means it makes it richer or leaner depending on what the actual sensor is reading. In a normal standalone ECU, if you didn't program that, it would just run off of the VE table, and there's nothing really that is changed except for some things, for example the barometric sensors or the battery voltage, because that can also influence on how the injectors are opening. But for example, if you have a car that, for example, runs ITBs, or under some instances on turbo cars also, it may happen that the manifold pressure is not actually the same across different load states. For example, on a ITB car, the manifold pressure is a lot more often close to the 100 kpa or close to atmospheric, although you are not giving it full throttle. And this is very important, where Lambda control can come in very handy. Or another thing that I show in the next video, but Lambda control can help in this instance to kind of be of help and adjust accordingly to get the fuel mixture right, because otherwise, if it's, for example, perfect on part throttle, but the manifold absolute pressure or the manifold pressure is already at atmospheric and you are only at half throttle or quarter throttle even, and then you give it full throttle, some more air may enter the engine and then you are going to run lean. And this is again where Lambda control comes in. It will add fuel if it sees that you are running lean. And I will show you the settings now, and then we're also gonna take a drive and I'll show you how that actually works. Now on to EGO control. Here there are not as many options. Obviously you need a wideband AFR sensor, otherwise you won't be able to use this. Sensor type is going to be wideband. As for algorithm, I don't really like the simple algorithm. It doesn't work that well. It's pretty slow. That's why I always choose the PID algorithm. And ignition events per step, I always choose 16. You could also go down to 12 or higher, but it's just going to act slower if you choose higher, and it doesn't really need to be anything lower than 16 or 12. The control authority is pretty important though. This is how much the controller can adjust up or down. So it can adjust the maximum of 16% up or down. So it can reduce the amount of fuel by 16% or increase the amount of fuel by 16%. This can be important or can be really beneficial when you are, for example, in an area that has really high mountains and
goes down to sea level again. For example, here in Greece, that's very often the case. I can drive like 20 kilometers and I'll be at 1000 meters above sea level, and then back again and I'll be at sea level again. So this can be very handy if you, for example, tune by map and maybe your barometric correction isn't set up that well, and also can be quite handy if you, for example, have an ITB turbo setup, because ITBs can be, if you tune by map, can be kind of iffy in pod throttle, and they tend to go rich or lean depending on how you have tuned it. So I would leave that at 16 if your AFR target table is good. What is that controller going to reference? Well, it is going to reference the AFR target table that you have created. It is going to look at these values and look at the current AFR that you are running and then adjust the fuel accordingly. So basically it is going to reference this as a driver's wish lambda or AFR value, whatever. Then only correct above AFR. This is self-explanatory. It's only gonna correct above lambda 10 or AFR 10. Anything richer than that, it is not going to correct. You can play around with these values depending on what you want to do. Correct below AFR 17 is pretty good, because you don't want it to correct when you are on deceleration, for example, and your AFR goes to 25 or 30 because the engine is not injecting fuel, and then you don't want your engine to, or your ECU to add fuel because you set the lower limit too high, and then the engine starts to inject fuel again, which doesn't really make sense. This is just the lambda value of the same thing basically here. Active above coolant, this is pretty good, because obviously you are going to have a startup sequence, or rather a cold enrichment, so that when your engine is colder it is going to run richer, and the wideband control or the EGO control is only going to be active basically from a specific temperature onwards. Active above RPM, this is kind of interesting, but I don't really use it that much. I set it to the lowest it can go, because I also want the sensor to, or want the ECU to correct my idle, so that the idle is going to run at a fixed lambda value. So I don't really use this, but you could say that the AFRs are only corrected above a certain RPM, and the same goes for TPS. So if you don't want the ECU to correct anything at full throttle, for example, then you can leave this like at 70% or at 80%, and full throttle won't be corrected then. You just have to watch out that your full throttle tuning is good. EGO delay after start is pretty important, because when the Lambda sensor is heating up and not showing a signal in Tunerstudio, it's going to show 0 volts, so usually about AFR 8. And if the EGO control obviously see this, it's going to tell the engine to lean out, so it's going to reduce the amount of fuel, and your engine is probably going to turn off because it's running very lean then. So you need at least the same time the AFR sensor needs to heat up. I would recommend a bit longer though, usually 30 to 40 seconds should be plenty. The PID settings, those are kind of tricky to get right. I will put a screenshot in the video of my settings, which work pretty well, but this is still something you have to try around with. I will link a video on what PID is exactly, that is explained down below, as I am not really that great at explaining this. So yeah, this is basically how the control acts and how fast it reacts to changes. And now I'm going to show you a short sequence of how the AFR or how the EGO control is working while driving. You can see the target and the actual AFR values, and you can see at the EGO enrichment or EGO control how much the ECU is subtracting or adding fuel. Unfortunately, I have forgotten to plug in my microphone, so there is no audio on this clip, but you can still see what I am saying or what I'm telling you. And you can see the effect that has on the car and on the AFRs. While yes, you wouldn't need that if you would have tuned your AFR or your VE table to perfection. The surroundings are always going to change a bit, even if it's more humid, even if it's colder, if it's hotter. While yes, you can kind of compensate for intake air temperatures, you cannot compare for density, for humidity, etc. So the PID or EGO correction is always handy to have working, because it can save engines, especially if, for example, it is a very dry but very cold day also, and the car is running very well and there's a lot of oxygen in the air. The car might run lean and the EGO control might save you from this. So I think it's one of the most important things to get your car running safely, and makes it also a better daily driver, as you are easier able to pass smog tests or emissions testing. Alright then, that's it from me for this video. I hope you learned something. If you have any questions, leave them in the comments down below, or ask me a message, ask me on Instagram or whatever. I'm always open for anything. And yeah, as always, have a nice day and goodbye.